The basic way of delivering this class, and hopefully this works for you guys, is I'll be putting up some videos of just the lecture. So there'll be the lectures with the lecture notes available to you, and the normal class time if we were to actually have a real class, which is at 10:30 on Mondays, I believe. I know it's a little bit accelerated because we didn't technically have class. Yeah, so I'll put up the videos, and then within the lecture notes, there's these embedded problems. So hopefully you guys have a chance to go through and try the problems out on your own. And then on the Wednesday class, then we'll just go through the problems in this format. People are still showing up here. So let's get to it. What do you think? Super fun? Okay. So I'm gonna try to change my video. I had it all set up before, but who knows what happens here. Basically, what I'll have, you'll see it, and I'll describe it here as I change it here. Yay! Oh, let's see now if I can see it. There we go. You can see my lovely pen and paper here. You'll be able to see what's going on, hopefully. I can see it somewhat, but if you guys have any questions or anything during
Are we taking notes on this?
Pardon me?
Are we taking notes on this?
You don't have to take notes. I'm just running through the problems that were embedded within the in the lectures. So you should have access to the lecture notes as well as like the video. Like I tried to do it, I don't know.
Oh, you did a video before this?
Yes, yeah. There's 2 videos that are up of the lectures. So I guess traditionally they had presented.
So we just have to view it like a couple of hours before the class?
So as I was saying before, but that's okay. I know it's all new. What the plan is, I'm gonna try to get the lecture videos up by the Monday at 10:30, which is your normal, if we were all together, it would have been the normal class time. So there'll be like lecture video with the notes available.
Yeah.
And it's not over, I mean, I could be a little bit biased, but it's not the first, so there's 3 videos up right now. There's, here, I'll just switch it back so you can see me. Probably not super fun watching notes, but yeah, so the plan is on the Monday I'll have the lecture videos up. I guess, oh, here's the chat, perfect, good. 2 videos, 3 videos, there's 3 videos, yeah. So there's just a welcome video, just, you know, describing the course outline, which is available too in PDF on D2L. There is, and then there's 2 lecture videos. Basically, the lecture videos, within the lectures and in the notes, there's problems. So the first bit will just be, sorry if I'm repeating myself here, will be just me doing the lectures, and then this, on the Wednesdays at 10:30. It'll be the same Zoom link for all of them, but I have been putting out, I'll email you the links every time too, just in case you lose it, usually about an hour before class starts. And then we'll just go through the problems that are embedded within the lecture and lecture notes. If you haven't seen the videos yet, that's fine. It's, you know, the first week is always a little bit not quite as challenging of materials. So the first videos are just describing the basics here. I'm just gonna, got them up in my own screen. Hopefully you guys have access to it. If you have D2L, you can open up the lecture notes. They're in PDF there. Oh, okay. Sorry, like I said, I'm still getting used to it. So the first, there's 2 lectures. The first one's just describing fluid properties and pressure. You guys probably have had a lot to deal, and learned a lot about pressure and different mechanical properties too. You guys have all done mechanics of materials, I assume. So you kind of know basic concepts, units, and variables. I am recording this and I'll put it up on D2L as well. So far, what I have been doing, my method of communication to you guys is I usually put up like a news item on the D2L, and I'll send you an email too. So then you kind of, I don't know, it might be too much communication for you guys, or it might be just the right amount, or it might not be enough. But yeah, that's usually what I have been doing, just like, so you get it in your email so that you know something has been put up. And then you don't have to keep checking D2L if you, but it is up there. Okay, does that make sense?
Good.
So if you haven't looked at the videos, you know, life will go on. All I'm doing, I'll describe the problems. They're just directly from the notes. And then we'll just run through some calculations, okay? Super
Yo.
fun.
Calculations on first day.
Pardon me?
Calculations on first day.
Yeah, they're not, I mean, to me, they're not overly intensive. It's basically finding different fluid properties. I mean, just absorb it. You can do notes now. I am going to, like I said, I'm going to post this. The hope is that you guys go through the notes, try the problems beforehand, before the Wednesday, just so that you can get it in your own head, and then, but I'll run through them. There is weekly assignments too, so after this session, I'll post the assignment. It'll be due next week, or Wednesday, sort of what I'm calling a study group. I'll post the solutions too, the ones that I've hand done, as well on D2L, so you have access to that. So, but like I said, whenever I post anything, I'll send you an email, as well as put like a little news item on D2L, and hopefully that works for you guys. Okay. Okay. So I'm just gonna switch. Lovely little video here. Hopefully it's not flipped out. I tried to change it so that I could see it, and the video quality is not super hot, but life goes on. Life goes on. Hopefully we all work for it. So if you guys have any questions or need some clarification on how the delivery of this class is proposed, I know it's a little bit weird given that Steve's doing the labs and I'm doing the lectures, but Steve and I do talk, so hopefully it'll be integrated pretty good for you guys. Okay. So if you open up, if you go to D2L and you open up week 1 fluid properties and pressures, the first unit, it's called unit 1. I'm just gonna, you can go through the notes in your own time if you haven't had a chance to review them yet, but I know we have a short period of time, so
what's it called?
It's called Unit 1 Fluid Properties and Pressure. It should be in week 1 folder in the content.
Okay.
Do you see it?
Okay, unit 1. Okay. All right, we got it open.
Excellent. So I mean, you can go. There's a video. There's a and there is these. We can go through it later, but basically we're just talking about different properties of fluids. So, you know,
Yeah.
just for those of you who haven't seen it, mind you, it's taking a bit to load, maybe because everybody's trying to open it up right now. But it's just, you know, specific gravity, specific weight, density, pressure, how to calculate pressure in a fluid. It is, I mean, again, like I said, it's a little bit, it's not too intensive. So hopefully you don't find this portion too intensive, but if you haven't had a chance to look at it. But like I said, it's recording, just relax. If you want to take notes, you can go ahead and take notes, but it'll all be up there to save on paper. It depends on how your brain works, right? Some people, how they
Write it
utilize them.
down.
Okay, so Unit 1, problem 1. Here we go. Are you ready? So a tank of water is open to the atmosphere. It's indicated by a little triangle on the surface. So, I mean, that's quite common. You'll see this sort of thing all the time. I have to do, like I said, I do a lot of like water. I'm coastal and marine engineer. So there's a lot of times you'll see this little triangle with these little lines. It's just to denote that it's water, it's the top of the water. And you can kind of see it in the notes there. Water is at 4 degrees C. So you'll note from the video and in the notes, and I'll just reiterate it, that fresh water is its densest at 4 degrees C. So it's kind of got some fun little implications, but for now, you don't need to know too much, but water at 4 degrees C has got a density, we'll figure it out. So find the volume, density, mass, weight, pressure on the surface it's sitting on. So here we go. I'm just gonna draw it out here. They've got a vessel. And for those of you who had the pleasure of doing my mechanics materials course, you'll know that I am very terrible at drawing, unfortunately. Okay, so hopefully, I think you guys can see that.
Sorry, you can't see it. It's too blurry.
Is it too blurry?
Yeah.
Fiddlesticks. Okay.
I suggest using a Sharpie as our statics.
Sure, yeah, that'll work. I got some right here. That's perfect. Thank you. Yay. Okay. So it says to find the volume, density, mass, weight, and pressure on the surface. So here we go. My terrible drawings. Is that better? Yeah, somewhat. It won't overcome my terrible drawingness, but you know. So we've got this little surface. Okay. One little vessel, and it is, so from the height of the water, it's 1.7 meters. The depth of the vessel is 1 meter, and the width is 1.3. Okay. Good. So the volume, first thing, volume. So volume, I guess you guys may or may not know, is usually in length cubed. Usually in our course, it'll be either in SI units, meters cubed or millimeters cubed. Usually meters cubed for fluid stuff, or feet cubed. It'll be usually pretty clearly defined. This problem is already defined in meters, so we'll just keep it in meters. For those of you who haven't had the joy of meeting me yet, you'll soon find out that I hate imperial with a passion. But here we go. So volume is basically, I guess you guys probably know this right now, is just going to be the height times the width times the length. So 1.3 meters times 1.0 meters times 1.7 meters. Okay. Got my trusty calculator here. So 1.3 times 1 times 1.7 equals 2.21 meters cubed. Mystery solved. That's the first bit. Second part of the question is asking us for the density. So that's denoted by, let's see that, yeah. Rho, okay. So if you look in the back of the book, or you can look it up on the internet, or you can.
The notes?
Pardon?
In the notes?
It's in the notes, I think, the density of water. It is in the back of the book too. The appendices has, you grab the book here. Oh, it's sitting on there. In the appendices, there's different properties of different fluids. So not just water, there'll be all sorts of different properties.
Is that in note?
It's in the book, the back of the book.
Okay, not in the notes though.
No. Well, I think the density of the water is described in the notes, but it is something you will quickly memorize because this is part of the reason why I like
The formula sheet.
there's a formula sheet there too. Yeah, I'm not sure if it's on there. I haven't memorized the formula sheet yet. But the density of water at 4 degrees C, part of the joys of SI units is that it's just 1,000 kilograms per meter cubed.
Yeah.
I mean, it's simple, right? It's not like for water at 4 degrees C. Water changes its density depending on the external pressure as well as temperature. And there is, in the appendices in the back of the book, there is a table that has different densities of water at different temperatures. But we'll get into that. We'll get into that later too. So don't worry about it too much right now. But I mean, it's pretty easy little number to remember. Okay, so that's the second thing, the mass. So if you recall, mass will be in kilograms. So the mass, and it's denoted by a lowercase m. So you guys can see that. Let's have a look. See. Okay, there we go. I'll flip the page here. So the mass.
That's the density, 100 kilograms per meter cube. That's it.
Correct. Yeah.
Okay, that's just the unit. Okay. Cool.
I told you it wasn't an overly intensive calculation today, this first week. So, and it's not even a calculation. It's just something you look up in the back. So
Yeah.
the mass, it's in kilograms, and it's equal to the density times the volume. Okay. So we've got the density from the last portion. So 1,000 kilograms per meter cubed times the volume, which was 2.21 meters cubed. Take out our calculator. 1,000 times 2.21, or you can be a little bit smarter than that. I don't think you necessarily need your calculator for that one, but hey, whatever. So you'll notice that these meters cubes cross out and we're left with kilograms, right? So that's another thing and to note for this class and for all of them. Write out your units for all the calculations, because usually what happens is if you come up with the right units at the end of the question, then most likely your answer is right. Okay, so what else is this asking us for? The mass. So we've got the mass. Now it's asking us for the weight, which is the force, right? One's the measurement of force, and one of them's a measurement of just how much something weighs, or how much. One's like dependent on gravity. So gravity will change depending on where you are on Earth or if you are on Earth. Okay, so weight, it's denoted in this class by a lowercase w. It's equal to mass times gravity. So we've got the mass, right? 2.210 kilograms. And gravity is 9.81. Let's just start it over here. The joys of Sharpies, I guess. 2.21 or 2,210 kilograms times 9.81, and gravity is in meters per second squared. Okay, so we go 2,210 times 9.81 equals, what do we have here? 21,680 kilogram meter per second squared. Now, I'm not sure if you guys have done this before, but you know that this unit here, kilogram meters per second squared, is a Newton. So this is equal to 21,680 newtons. Also, to the joys of the metric system, we divide this by 10 to the 3, get 21.68 kilonewtons. Hopefully that's not a big surprise to you by now. Okay, so we've got the weight. The next thing that it's asking us is pressure that pressure on surface it's sitting on. So if we go back, when it's asking for the pressure in which it's sitting on, it's just the bottom of the vessel, okay? It's a little bit weird wording, but we'll get used to it. Flip. So E, pressure. So the pressure in this course, I guess in a lot of courses you probably have seen it as a capital P. In this course, it's just a lower p, so that looks like a rho. So it's equal to force over area, which is equal to the weight over the area. Okay, we solved the weight in the last question. Isn't that convenient, eh? Everything's all nice and easy. So we got 21.68 kilonewtons over that area. So if we recall our lovely little vessel, it's 1.3 by 1.0.
What if you use newtons instead?
Oh, that's fine. Yeah. Newtons is fine for sure. Yep. As long as it's clearly, as long as you clearly state it, right? I mean, you could report these in imperial units. I will not like it too much. You just, and there'll be a lot of like conversion, but it doesn't, it's all good. Yep. So kilonewtons, and we've got 1.3 meters by 1.0 meters. So we'll divide 1.3 times 1. And what do we get here? We get 16.68 kilonewtons per meter squared. 16.68, or otherwise known as 16.68 kilopascals. It's denoted by kPa. Yay, first equation solved. Okay.
That was pretty easy.
For me,
That was pretty easy.
I know, like I said, it's not like a, you know, we got to warm up too, right? Can't just immediately go into a hard problem. So if we look on, okay, I don't know if I clearly stated this, but let's do it now. Just so that you know, so we're on page, it doesn't tell me what page we're on. Fiddlesticks. Okay, so problem 2. The fluid is oil with a specific gravity of 0.92. Find the volume, density, mass, weight, and pressure on the surface of the cylinder it's sitting on. So problem 2. If we look at the cylinder, here it is. Okay. What do we have here? So we've got, here we go, another little triangle. It is 2 meters deep, the fluid, not necessarily the cylinder, right? It's 0.5 of a meter in diameter. So first thing it's asking us for is the volume. Sorry, it's a little bit wiggly. My camera's on a weird little tripod that I picked up, so it's suspended in the air. Hopefully it doesn't give you too much motion sickness. So the volume of the cylinder, you may or may not know, but it's easy to find in various references. It's pi over 4 times d squared over the height. Okay. So we got pi over 4. The diameter is 0.5 of a meter squared times the height, which is 2.0 meters. Oopsie, meters. So 3.14 divided by 4 times 0.5 squared times 2. You've got 0.393 meters squared times meter is meter cubed, which is the unit for volume, right? So good to go?
Yes.
Yay. So next thing, B, they're asking us for the density, rho. So that's equal to the specific gravity times the unit weight of water at 4 degrees C. So they're telling us, they already told us that the specific gravity is 0.92 times 1,000 kilograms per meter cubed. Like I said, you'll quickly remember this number. It keeps coming up over and over and over again. And it's relatively easy. So you can use your calculator or your noggin.
Does that say S times G?
Yeah, well, specific gravity is just denoted as SG. That's all. So it's just like this is one thing, and then this is another thing. Makes sense? So,
What's the unit for this? kg. No.
pardon me?
What's the unit for this?
Oh, specific gravity is unitless, which is another great thing of it. It's just a ratio of the fluids, either the ratio of the fluids density.
We found is
compared to-
density, right?
Yeah, compared to the other, to a density of another fluid, and generally, for our purposes, that what you're comparing it to is water at 4 degrees C. So always 1,000 kilograms per meter cubed.
Okay.
If you know, become some sort of, I don't know, crazy scientist, you might be looking at specific gravities of fluids with relationship, I don't know, to mercury or something. I've never seen it, but it could happen.
Oh, let's stay on Earth.
Yeah, exactly, exactly. So for the purposes of this course, it's always going to be water. It's always going to be 1,000 kilograms per cubic meter, unless you deal with imperial units.
Okay.
Is the density, is it 32 point, no, that's how much it weighs. Yeah, 32.2 slugs per foot cube.
What does density mean?
It's in the notes, but
What does density mean? Like what we found? What is kilograms per meter cube? Like,
so how the density of a fluid or a density of anything, I mean, it can be, you know, a cake, it can be steel, it can be whatever, any kind of material, any kind of matter, is how much mass per volume it is. So in this case, this oil, if you had a cubic meter of oil, of this oil,
yeah.
then it would weigh 920 kilograms. Same with the water, right? It's just so if you had a cubic meter of water, fresh water at 4 degrees C, it would weigh 1,000 kilograms.
Yeah. Okay.
So the specific gravity is just a ratio of that.
Oh, of the oil. So oil is essentially lighter or heavier?
Yeah, exactly. Yeah.
It's lighter?
Yeah. Good observation. Oh, you just made me so happy right there.
Yeah. So oil is lighter? That's kind of hard to believe. I thought water was lighter.
It depends. It depends on what the specific gravity of the oil is, right? That's why everybody gets all weirded out by that bitumen. I don't know if you guys followed much of the that proposed pipeline that was going to I think Kitimat, right?
Is it still going?
I think so. I think so. It appears people have jobs doing it. So, but that was part of the problem, right? When if they're worried about if the oil spills, that because it's denser than the salt water,
Oh,
that it'll sink to the bottom and kill all the starfish or
oh.
whatever. It's harder to collect all sorts of different things.
Do we need starfish?
We need starfish for sure. I'm not exactly sure what for, but I remember even just like a couple years ago, there was that starfish wasting disease. Anyway, I digress. Back to, there's a few of these problems, but yeah, it has a lot of implications. I mean, it's the same, for fluids, we're not just dealing with fluids, there's also gases, so air, right? So there's certain times where a gas will be more dense and it sort of sits on the ground, or it's lighter and it sits in the air kind of thing. Anyway,
That's the most dangerous gas.
yeah, well, it depends, right? Like, it depends because there's natural gases within air too, natural impurities within air. You can still breathe it, but as long as it doesn't get too bad. Any which way, where are we? So we got the volume, we've got the density. Now we're gonna check out that mass. Okay, we can see that, good. So the mass again is a lowercase m, and it's calculated by using the density times the volume. So we've got that density, 920 kilograms per meter cubed times the volume. Where is it? Where is it? There it is. 0.393 meters cubed. Push. So 920 times 0.393 equals, what do we got here? 361.56 meter cubed, crosses out, kilograms. Good to go. The next thing that we're finding is the weight. So lowercase w is equal to mass times gravity. You might also recognize this as force equals mass times acceleration. Okay. What do we have? So we've got the mass, 361.56 kilograms times gravity, 9.81. Geez, I always forget the units in this, meters per second squared. Of course, it's acceleration. So times 9.81. Oopsie, got the 9 in that one. Times 9.81. So 3,500. Still see it good. 46.90 newtons. 1, 2, 3. There we go. 3.1235 kilonewtons. Next thing. Speaking of oil, a little oil truck just went by. Okay, so next one is pressure. So lowercase p, again, that's going to be some I'm going to have to get over, is the force over area, weight over area. What do we have? 3.5. I don't know, let's use a million decimal places, why not? Divided by pi over 4 times d squared. So what is this, kilonewtons? We got 3.5469 kilonewtons over pi 4, 0.5 meters squared. So 3 point, what do we got here? 547, sure, divided by 3.17 or 3.14. 4 times 0.5 squared. So that 18.06. So this will be kilonewtons per meter squared, kPa. Easy peasy, fresh and breezy. Next.
So on the test, it's going to be similar questions like this.
um, probably, yeah. Like
Awesome.
the tests are going to be very similar to everything that we do, like the assignments
In class?
in class, yeah, and in
Awesome. That's
so
good.
it shouldn't be. It's not. I'm not here to trick you.
That's good.
Yeah. I'm not. I mean, obviously some things will be harder than others, but yeah, I'm not here to freak you out or anything. There's two, if you kind of look at that video, there's going to be 2 midterms and a final, just to try to alleviate the pressure of these classes, to help distribute some of the marks, so that it's not like 1 midterm and 1 final and freak you out. So the final usually used to be worth about 50% of the course.
Yeah.
In this course, in the outline, I think I made it 30%. So you got 2 midterms that are both 15% each, and then the final. I mean, you have to do all the assignments and all the labs in order to write the final, and you have to pass the final.
Okay.
In order to pass the course, 60%. But yeah, it's not. I'm not gonna give you a question that you haven't. I mean, you might see it might be a little bit harder, but it won't be something you haven't seen before. I mean,
That's very reassuring. Thank you.
Yeah, this is the first fluids course you guys take too, right? This isn't like the second one you take. Sorry, not super familiar. Yeah, so it's not gonna be. Yeah, I'm not gonna ask you something that you like. Second.
Who taught this class before?
You have had this class before?
No, somebody taught this class before you.
Oh, yeah. Oh, yeah. I think everybody's taught this class before me, all the faculty. It's my first time, so please be patient.
Yeah.
Thank you for giving me the Sharpie. So here we go. Problem 3. An unknown material has a mass of 340. So we've got problem 3. We got a mass of 342 grams and a volume of 1 point. So this is the mass, little case M, volume of 1.8 times 10 to the negative 4 meters cubed. Well, these are fun units. This is where it starts getting fun. Find the density, specific gravity, weight, and specific weight of this unknown material.
That, right?
Pardon me?
There's a formula for that.
Yeah, that's all in it's all in the notes. But we'll go through it right now too. So
Okay.
yeah, maybe next week might be a little bit more it's going to be more intensive material, but make a little bit more sense because you guys would have had a chance to go through the notes and the video too. So density. So that's equal to mass over volume. We've done this a couple of times now. So they've given us the mass. Now you'll note everything's in like sort of strange units. So you probably know that a kilogram is just 1,000 grams, but if not, there it is. So 0.342 of a kilogram. Because these are the base units, kilogram, meters cubed, like, that's the base SI unit. So so the volume is 1.8 times 10 to the negative 4 meters cubed. Take our best friend, Mr. Calculator, or Miss Calculator. I'm not sure what the French and or Spanish genderization of a calculator is, but here we go. So we've got 1,900 kilograms per meter cubed. So that's its density. The next thing that it wants us to do is the specific gravity. So that's denoted by an SG, S dot, G dot. And that's just a ratio of its density over the density of water at 4 degrees C. So we got 1,000, we've got the density of this unknown material cubed over 1,000 kilograms per meter cubed. So, and as stated, specific gravity is unitless. So 1.90. Now, if you're an inquisitive person, you probably could go look in a book and try to see things that have a specific gravity of 1.9 and try to figure out what this unknown material is.
Wait, what? Like, how'd you know that it was 1900 kilograms per meter?
Because we calculated it in the first step.
Oh yeah, right.
Yeah.
No. Okay.
So see, the next thing is the weight. So the weight, the lowercase m, is equal to the mass times gravity. Okay, we've got the mass, 0.342 kilograms times 9.81 meters per second squared. 0.342 times 9.81. What do we got here? 3.36 kilogram meter per second squared, or we can just go straight to it. 36 newtons. So that's one way to figure it out. I mean, this is just how we did it. The other way that you can figure out this weight, and if you look in the notes, you can see that the weight is also equal to the specific gravity. What is this little u? I can't remember. It's times the volume. Specific weight? Yes. Specific mass. Any which way. So you can do it that way too. But whatever. This is how we did it. Where are we on? Flip the page. Next thing we're looking at is the specific weight. Yeah, there we go. So the specific weight is this little gamma, excuse my Greek lettering, which is equal to rho. So this, the density times gravity. So 1,900 kilograms per meter cubed times 9.81 meters per second squared.
A specific gravity?
Yes, this is the specific weight.
Specific weight.
Yeah. So there's a couple of different properties of fluids that we look at, and one of them is the specific weight. There's a couple other ones in there too. It's all in notes, but like I said, don't just go back and review it, and there's a table in the notes that goes through it all and what the units are for each one too. So what do we have here? Oops. So 18,639. What do we have here? Strange little units. Kilograms per meter squared.
That B, like, that B?
For me?
That B? Like 1B?
This is a D, so this is the last
No, that's one.
the last bit that they're asking us for.
And the answer.
Oh, the answer. 18,639. Yeah, I made the joys of Sharpie, I had my eraser, but that's not going to work for this.
8,639.
Yeah, so we've got kilograms per meter squared, second squared. This is just such a weird little unit, isn't it?
So how is specific weight different than regular weight? Like, why is there second, like, time in there?
Sometimes you care about, why do we care about this? lots of times it's used in, you'll find this too. Have you guys done soils yet?
Yeah, I passed that. Like, but like,
Yeah, so
I
lots of
taught
times.
it in too, but I just didn't understand what it was.
Okay, yeah, it's just this comes out into, basically we've got, if we look at this, it's 18.64 kilonewtons per meter cubed. So maybe this might make a little bit more sense if we look at these units for you.
Oh,
You know,
yeah.
it's basically how much the weight is. So in
That makes
gravity
more.
on Earth per cubic meter. So basically, if you had a cubic meter of this random material, it would be 18.64 kilonewtons. That's how much it would weigh if you had a cubic meter of it. So a lot of times, what do we care about this? Lots of times it has to do to help figure out pressures on things.
Yeah, yeah.
Okay,
Cool.
okay. I don't. Hopefully we'll get through this. Here, that was the lot. So now we've got, problem 4. Motor oil has a specific gravity of, I mean, I don't mind going over time if you guys are okay. I don't know if you have classes after this.
Some of us do at 11:30.
Okay. What I can do,
Some of
like I
us,
said, I'll publish all the answers for you guys. And if you guys, I'll just stay on and continue the video so you guys have it. Hopefully it doesn't, we'll see. There's a lot of problems in this one, but I mean, they're not, like I said, they're not too labor intensive. So problem 4, motor oil has a specific gravity of 0.887 in a volume. What volume would have a weight of 12 newtons? Okay, this is interesting. So problem 4, what do we have? We've got SG, specific gravity, is equal to 0.887. And we want it to weigh 12 kilonewtons, okay? So if you go through the notes, you'll see this. Gamma equals weight over volume, okay?
Where did you get the 0.887 from?
It's in the problem.
Oh.
So it's a problem 4, motor oil has a specific gravity of 0.887. So what do we have here? So what are we trying to find here? We need the weight of this thing. Specific gravity is equal to, this is basically a ratio, not just the density of, but it's also a ratio of the specific weight of the material over the specific weight of the water at 4 degrees C. So what can we do here? What do we know? We can do this. We can have the unit weight. Hold on a second. Sometimes it shifts and I can't. Okay, I just want to make sure that you guys can see what I'm doing here. So I have to have my camera up as well. So we've got the specific weight is equal to 0.887 times the density of the specific weight of the specific weight of the of water at 4 degrees C, which again you can look it up in the back of books, or you're going to quickly memorize this too. It's 9.81 because it's 1,000 kilograms times.
I thought it was 1,000.
Yeah, that's the density. So the density of water at 4 degrees C is 1,000 kilograms per meter cubed.
Specific.
If you do look at the specific weight, it's just here. Hopefully you can see this here. It's basically of water at 4 degrees C. It's going to be 1,000 kilograms per meter cubed times gravity.
Oh, okay.
That's all. And that's covered in the notes. Yeah, if you guys didn't watch it, no.
All right.
Yeah, but that's covered in the notes. Again, these are just things that you'll be using over and over and over again. So they will stick in your head eventually. Don't get too worried about it at the moment. So what do we have here?
Because every time it looks like a dead end to me, and then there's another formula.
Pardon me?
Every time it looks like a dead end to me, and then there's a formula.
Yeah, it would have helped, but I mean, it's totally understandable that you didn't see it yet here. So where do we go here? So we've got specific weight 0.887. What is that? It's unitless times 9.81 kilonewtons per meter cubed. Okay. So what do we get here? 0.887 times 9.81. 8.7 kilonewtons per meter cubed.
How do you know it's kilonewtons per meter cube? Why is it not newtons? Like, where'd you assume?
Oh, just because the ratio of the unit weight or the specific weight of water
Yeah.
is 9.81 kilonewtons per meter cubed. Again, you just get that in a book, like in a table. Yeah.
Good.
Similar like how we, not that we did it physically, but if you looked it up in the back of the textbook or even on the internet, again, you guys are smart enough to know not to believe everything you read on the internet. Usually what I've had to do is try to find 3 sources and then to verify that it's true.
Yeah.
Okay, so we've got 8.70 kilonewtons per meter cubed. And the volume.
That's the specific density?
Yes.
Okay.
So what do we have here? The volume is going to be equal to the weight that we want divided by this. Divided by.
What are we looking for now?
We want to know how much volume is needed to weigh 12 kilonewtons. So the volume is equal to that 12 kilonewtons that we want, right?
Yeah.
Kilonewtons? Or no, sorry, 12 newtons. So this is in kilonewtons, they want it in newtons. Oh, joy and bliss. So we've got 12 kilonewtons divided by, what do we have here? If we do this in equals 8,007. Is that times 10 to the 3? Yeah. Oh, that's nothing.
Do you mind doing it a little bit underneath? Yeah, I don't understand. Are we gonna do 12 newtons divided by?
Start again. Fresh. Does that help? So the volume is equal to 12. They want newtons. Okay, that's right. And we're going to do, what did we have here? Specific weight is equal to 8.7 kilonewtons per meter cubed. We need to make this into
Did you get 8.7 kilonewtons?
newtons per meter cubed, just so that we've got our units right. 870. 1, 2, 3. 1, 2, 3. Yeah, 70 newtons per meter cubed. 12 divided by 8700. Oh, stupid calculator. We get 1.378 times 10 to the negative 3 meters cubed. One thing, I don't know if you guys have learned this yet, but I'm going to tell you now. So 10 to the negative 3 meters cubed is 1 liter. So the volume that we need is 1.38 liters. Holy moly.
Wait, what? Up a little.
Did I just jump too many steps there for you guys?
Yeah, it was a little fast.
Okay. So if you if you watch the video, it goes into a little bit more about the basis of units that we need.
Okay.
And one of the things is, yeah, for volume, it's meters cubed. An alternate unit for meters cubed is also liters. You guys probably have seen a liter of milk, right?
Oh yeah.
Because a cubic meter is pretty giant. You can imagine having a meter stick, length, height, and width. It is kind of a big unit for a liquid or gas. So
Yeah.
alternatively, we use these liters. So
Got it. I
yeah.
was you just introduced the concept. I was like, what's happening? Weird thing.
Gotcha. Yeah. So
Cubic-
and so a liter is just 10 to the negative 3
Yeah, that makes
meters cubed. That's all.
Yeah. Okay.
Lots of times it's easier for people to wrap their head, like it's a lot easier to think of a liter because we're familiar with liters.
Yeah.
Not until you start working with it a lot, you're not super familiar with what like a cubic meter actually looks like. And it is kind of giant. Well,
Yeah.
I mean, big enough. Not like something you wouldn't have like a cubic meter of whatever hanging around, maybe a box.
Is that number 1.38 liter?
Yes.
What
Or
is-
yeah. So when you do it for your homework or for homework or assignments or whatever, and if it specifically asks for a unit, like if it specifically asks for liters, provide it in liters. But if it doesn't, then giving it to 10 to the negative 3. There we go. Meters cubed or in liters, both are acceptable.
Okay. What was that calculation up top?
This guy.
Yeah. Okay.
This is just trying to find the volume, right?
Okay.
Because that's the heart of the problem, is trying to find the volume.
Newton over, like, what's the formula for volume?
But a volume is in meters cubed or liters or feet cubed, or it's just length. It's length cubed.
You put force over what here? Like,
Oh, this one happens to be, so to find the volume for this one, just how we went about going it, it's basically volume is equal to, the force over gamma. The trick for this one is that we had mixed units, right? We had kilonewtons and we had newtons. So it's just a little bit of a conversion joy.
okay.
Because usually this will be in newtons or slugs or whatever. And this will be in either newtons per meter cubed, or it could be, kilonewtons and kilonewtons per meter cubed. And so those cross off. This guy goes up to the top and you'll have cubic meters.
Can I peek on top of your sheet, like the top of your paper?
Oh, there's nothing there.
I forgot to write that down.
There's
Just
which is a bit messy.
no, wait, I lost it. It was the last paper.
Okay. Please hold while your request is being processed.
Last one we were working on there.
Oh, yeah.
2758 times 10 to the 3 meters cubed. Okay, I was just getting the volume.
Yeah.
Okay, cool, got it.
Okay, excellent. So I understand you guys have another class, and do what you got to do. I'll stay on, and like I said, this is being recorded. Good. So I'll post the video, but for those of you who want to stay, and we'll go through there's I think 9 problems in the first lecture and 2 in the second. So I'll just keep going. If it makes you happy, it makes me happy.
Will it make you happy?
Oh yeah. What else do I have to do but calculate some other junk? This is easy stuff. So it's a little bit it's not quite as difficult as the other stuff I got to do for other work.
I haven't done math in a year, and this is like a good start.
Yeah. So problem 5 for mercury, the specific weight is 132,800 newtons per meter cubed. What is the volume of a 92 grams sample of mercury? And what is the specific gravity of mercury? Okay. So here we go. So what do they give us? I have to get another, still okay, I guess, eh? So 132,800 newtons per meter cubed. Okay. So the specific weight is equal to the weight times the volume. So if we just rearrange this, the volume is equal to the weight times divided by specific weight. We also know that the weight is equal to mass times gravity. Correct. So what do we know? If we put these two together, you know the volume is equal to the mass times gravity over this specific weight. So what else do we have here? We know that the volume is 92.0 grams. So what do we have here? 0. Again, we got to convert this guy into the volume. Oh, what is the volume? I should have looked at that. I knew it was a little bit weird. So this is the mass, just from the units. It's obviously not the volume. I need more coffee, obviously. So 0.9202 kilograms. So we got to convert it into the regular units times 9.81 meters per second squared over specific weight, 132,000 newtons per meter cubed. So let's see what our volume is. 0.092 times 9.81 divided by 132,800 equals. What do we got here? 6.6. Oh, 6.796 times 10 to the negative 6. And let's see what our weird units are. This is newtons, that's meters cubed. This is newtons, right? And that's newtons, so we cross those off and get meters cubed. So that's a good sign. And what do we know? Because this is kind of awkward. It's 10 to the negative 6. And we know 1 meter cubed is equal to 1,000 liters from the last question, right? So this volume will either be 0.0068 liters. 1, 2, 3, 1, 2, 3. We also know, I don't know if you know this, but maybe you do. 1 liter is equal to 1,000 milliliters. I love metric so much. So what do we have here? It's also equal to 6.8 milliliters. Join bliss. So now we know what volume is needed for this.
Wait, it's 10 to the negative 6, right?
Yes.
So if you you move 6 decimal places.
Yep.
But you didn't.
Sorry. 1, 2, 3, 4, 5, 6. 6.7 times 10 to the negative 6, 1,000. Did I miss a 0 here?
It should be 6 from after here, and then 1, 2, 3, 4, 5, 6. There should be 3 more zeros in front of it.
That's for the meters cubed. I'm just converting it to, so I've got it reported.
I think you're correct. You've done it right.
Yeah. So we've got it in meters cubed. I've got it in liters, and I've got it in milliliters. They're just different units of volume, right?
Yeah.
I'll let you absorb that later. Okay, we'll keep moving along. So this,
Right. I know it's right. I just have to wrap my head around it.
sometimes it takes a while. I totally get it. Sometimes it takes a while. So the specific gravity, so that's asked us what volume. There it is, 3 different volumes. Well, same volume, just different units. The other thing it's asking us for the specific gravity of mercury. Again, you could look it up in a book, or specific gravity is also a ratio between the specific weight times the specific divided by the specific weight of water at 4 degrees C. So we've got the specific weight, newtons per meter cubed of the mercury, and we know that the specific weight of water is 9,810 newtons per meter cubed. You can see that still good. So 132,800. I have been known to make a calculation error. So if you do catch me on it, then that's great. It's sort of the importance of getting your work checked. I cannot stress enough in engineering and technologies to make sure that there's, you know, when you're working, proper quality control, quality assurance checks. It's very easy. I mean, everybody does it. We're all human, right? So that divided by that, 13.54. And again, it's dimensionless, these cross out. Good. Next question. 6. What pressure is the bucket exerting? So this is page 36, if you care. What pressure is the bucket exerting on the surface it's sitting on in PSI? Oh, yeah. Joys of Imperial. With no information is given about the fluid, assume it's at water at 4 degrees C. Okay, so we're going to assume that it's water at 4 degrees C. So it's problem 6. Boop. Got a cylinder. Again, boop. Little triangle, 1.5 feet. The diameter of the vessel is 0.7 feet. So what do we need? We need to know what pressure at the bottom here, okay? So pressure is force over area, which is also known as weight over area in this course. Okay. We also know the specific weight is the weight over a volume. We can rearrange this. And we've got weight equals specific weight times volume. Area for a cylinder is pi over 4 d squared. So pi over 4 times 0.7 feet squared equals, here we go, 3.14 divided by 4 times 0.7 squared. Got 0.385 square feet. You can see that's still good. So the volume is basically the area times the height, right? So we got that area, 0.385 feet squared times 1.5 feet times 1.5, 0.577 cubic feet. We know water unit weight of water or specific weight of water at 4 degrees C. If you look it up in the back of the book, it's also in the notes too. So 62.4 pounds per cubic foot. Again, it's one of those things that you start remembering after a while. But you can look it up, it's in the back of the book. So we've got the weight is equal to, remember this guy that we did? So what are we gonna do?
On the above, is that V or the gamma?
It's so the weight is equal to gamma times V.
No, the one that where we found feet cubed.
Oh, this is the gamma,
And then the one above that is
is the volume.
volume, right? Okay, perfect.
Yeah. One way, like, sometimes my writing's a little bit weird, but yeah, and you'll get used to it just from like doing it all the time. You'll get used to the units. So if you have a question about whether it's volume or specific weight or some other weird thing that I didn't write super awesome, it'll be in the units too. So volume is always length cubed. Specific weight is force over volume or a weight over volume. Okay, so weight. Here we go. 62.4 pounds per foot cubed times the volume, 0.577 cubic feet. 62.4 times 0.77. 36.0 feet get crossed off. Got pounds. Okay. Got the area. Good. Oh, they want it in PSI. So PSI is pounds per square inch, and we've got our area in feet squared. So let's just convert it now. I'm gonna flip the page. Okay, run out of room here. So our area before that we calculated was 0.3848 square feet. And how to convert it, I think it's in the notes too, but I mean, there's a couple different ways. You can either do, say, there is 12 inches in a foot, and this is squared, right? So squared. So 0.3848 times 144. We've got 55.41 inches squared. Okay, now the whole point is trying to find the pressure, right? So the pressure is equal to the weight over the area. And from our previous, did we have the weight? Yes. So 36.0 pounds over 55.41 inches squared. .65 pounds per square inch. That's PSI. For old people. Done. Good. Next. Number 7. Okay, let's see what this says. A liquid is oil with a specific gravity of 0.9. What's the pressure at 0.1 and the pressure at 0.2?
How many people are in this call still? More than that.
We're good? You have a question? Problem 7. So there's just like this weird little, who knows what vessel, some sort of weird vessel. It's been pressurized. So the little icon in there looks like a little tire pump. That's just to denote that it's been pressurized. So this vessel, it's been pressurized, and it's air, judging by at 50.0 kPa. So this is an additional pressure that's been put onto the fluid. So we've got 0.1 here and 0.2 at the bottom of the vessel. This depth is 2.6 meters, 2.60 meters. So the pressure at the surface is just going to be induced pressure. So P1 is equal to that 50.0 kPa. Before it was open air. So, you know, the pressure is just atmospheric pressure, and it's considered zero, sort of, depends on what unit to go into. We'll get into that later on, don't worry. But so now to find pressure at 0.2, it's going to be this induced pressure. So pressure at 0.1 plus the specific weight times the height. The only information that we're given is the specific gravity of 0.90. So if you recall, specific gravity, it can either be like, you know, the ratio of the density of the matter divided by the density of water, or the specific weight of this thing times the specific weight of water at 4 degrees C. We're trying to find specific weight. So what do we got here? We rearrange this equation.
Wait, where did you get the specific gravity again? Or
It's in the problem.
okay.
So the liquid is oil, specific gravity of 0.9.
Okay.
Where are we hiding? Okay, so times the unit weight of water at 4 degrees C. So we've got 0.90 times 9.81 kilonewtons per meter cubed. So 0.9 times 9.81, 8.83 kilonewtons per meter cubed. So the pressure at 0.2 is equal to 50.0 kPa. You can see that, okay, plus 8.81 kilonewtons per meter cubed times the height, 2.60 meters. Kind of see that? So 50 plus 8.81.
Can you explain again how you got 50 kPa?
It's kind of, it's written in the, if you look at the diagram, it's a little bit weird, this hand-drawn diagram. So it's just a contained.
Oh, I see.
Yeah, it's just got like this little these are Zoe's lovely drawings, I can tell. She's just got like a little bicycle pump. It's just denoting the fact that it's got like an induced pressure on it, pressurized vessel. So what do we got here? kPa, this will be in kPa as well. This is meters squared. What do we got? 72.96 kPa.
Holy shit.
So we solved the problem. Got the pressure at 1, which is that induced pressure at the top of the liquid. Pressure 2 is just the pressure already induced on it, plus basically the height of the liquid, the weight of the liquid above it, which happens to be oil. Okay. Number 8. Calculate the force on the shaded area from the water pressure. Okay. So
What was the
let's go.
answer for the last one?
Pardon me?
What was the answer for the last one?
Sorry, it was flippity flip. So the pressure at point 1 is that 50 kPa,
Yeah.
and the pressure at point 2 is 72.96 kPa.
Okay.
So like I said, it's just the induced pressure that's at the top plus the pressure caused from the liquid, the height of the liquid.
Yeah.
So the weight of the liquid times the height.
Yeah.
Okay. Calculate the force on the shaded area from the water pressure. Okay, so we got sort of a weird little L-shaped container. Again, I apologize in advance for my terrible drawing. But this is probably why I didn't go into drafting. So 2.9 meters. This height of the top leg is 1.4 meters. The depth is 0.8. And then this little guy is 0.3. It's water at 4 degrees C. And what are we trying to find? The force on the shaded area. So this bit here. Boop, boop. Okay, so we're been told that it's water at 4 degrees C. So specific weight, 9.81 kilonewtons per meter cubed. See, told you guys would learn it pretty quick. Okay, so the pressure is the unit specific weight times the height. And here, because we're only looking at this shaded, right? The height is at 1.4 meters. So the pressure is equal to 9.81 kilonewtons per meter cubed times 1.4 meters. 9.81 times.
Why are you using 1.4 again?
Because that's the because we're interested in the shaded part, so like basically the top of the leg.
That's the depth of that air, that surface.
Yeah, it's the height of the water above that surface.
Right.
Yeah, because I don't know if you had a chance to review the notes or look at the video, but again, it would have been
Briefly.
yeah. It's the pressure independent of the shape of the vessel. The pressure at any point within the
Right.
vessel is going to be the same, if that makes sense. And it's,
Yeah.
Okay, good. Okay, so where we got here? 13.734 kPa. This crosses this out, squared, kilonewtons per meter squared, kPa. Again, I do have a tendency sometimes to skip some steps.
Don't do it.
I will try not to, but yeah, I'm not going to write out kilonewtons per meter squared anymore. I'm just going to go straight to kPa. Hopefully you guys get that by now.
I'm confused with this question. Like, can you just kind of give me a gist of like what we're trying to do here? Like,
And so calculate the force on the shaded area of the water
okay.
from the water pressure.
Yeah, and the whole thing is underwater.
The vessel contains water. It's not like the vessel is underwater. So
Oh,
basically,
okay.
yeah. So the top of the water, again, I guess I could have done a little triangle there, but it's in the notes there as well.
I see that. Okay.
So
What are we trying to do? Like,
we're trying to find the force on the shaded area from the water pressure.
Okay.
Don't worry, we'll take it step by step, okay? So we found the pressure, right? Now we just have to find the force. And what's the force, right? So pressure is just force over area, right? So they're asking for the force. So if we just rearrange this equation, you get force equals pressure times area. So what's the area, you ask? The area is this shaded area. So what is it? 0.3 of a meter times 0.8 of a meter. Let's see, 0.3 times 0.8 is 0.24 meters squared. Yeah, and is it Maha? Is that, or
Yeah.
okay? It would have, this would have made a lot more sense if we would have had a chance to review the notes and the lecture video. But so
You should do that before and
be
then
a little bit weird for you because you're gonna go back and review it. But like I said, this is good. This is being recorded, so you can go back and review it all in your own time.
Okay.
Okay.
Yeah, I just didn't know that I had to watch a video before the classes.
Yeah, exactly. It would have made a little bit more sense. But have you been getting my emails?
No.
Oh,
This is the email I got.
you got
Yeah,
an email for this. Okay. So yeah, so on Monday, probably, when you might have not noticed, I sent out an email that said that there was videos up already. If you
Oh,
didn't- yeah,
let me check out again.
yeah. Don't worry about it. I mean, Monday was a holiday. First week is easy. Don't worry about it. It's all good. Okay. So we've got the area. We've got the pressure. Now all we have to do is go about and find the force. So force acting on this shaded area is 13.734 kilonewtons per meter squared times 0.24 meters squared. What do we got here? So these meters squared cancel each other out. You get 3.30 kilonewtons. So just also FYI, and you'll see this in it's probably kind of a weird thought, like, what is this force? What's happening with this force? Where is it being applied? How's it felt? If you were a particle on the surface of this vessel, you would feel it perpendicular to it. So the force and acting just at the, you might remember this from your mechanics of materials course. It's acting halfway, right in the midpoint. That's at 3.30 kilonewtons.
Yeah.
Just because sometimes I like to know, what's the actual physical thing of whatever this is. So this force is, 3.3 kilonewtons. So 3.3 bags of sugar pushing up.
It acts perpendicular to the surface?
Yeah. It's
On
just
the liquid or on the surface?
on the surface. If you're looking at the if you're looking at the particle, like the water particle, because say the water particle is just like slightly off of the surface.
Right.
It's all minutia of things now. If you're the water particle, you're experiencing this force in all directions, equally in all directions. If you're the surface, it's acting perpendicular.
Okay.
It's a little bit of a weird concept.
That was well put.
Yeah. Okay, good. Okay, problem 9. I think this is this is the last one for this. We still have a couple from the next portion, but here we go. Problem 9. Before any force is applied to the volume of a sample of machine oil, before any force is applied, the volume of the, okay, so before any force is applied, the volume of the sample of machine oil is 1 liter. So remember 10 to the -3 meters cubed. A force F is applied causing the pressure to rise to, cheese and rice, this one's fun, 4,000 PSI or 27,579 kPa. Oh, thank goodness that was done. Otherwise, we'd have to be doing all sorts of unit conversion. Calculate the new volume and the magnitude of the force. So remember, like if you watch the videos, but if you didn't, if you apply a pressure to a volume of gas or liquid, so fluid, it will change its volume. Liquids are a little bit less compressible than gas. If you think about, you know, like a compressed vessel for helium, you know, it's if you had like a bunch of water in there, it would be a little bit different than a of a volume than the water. Anyway, here we go. So what do we have? I'm just going to doodle this out. Perform your calcs in both metric and imperial. Oh, meanie. Okay, so we've got this vessel. Oh, 9. Okay, what do we have? This vessel, cylinder, 0.2 meters diameter. I know it's a cylinder because it's giving it to us in a diameter. So what do we have here? So force applied to it. So you gotta, this is kind of a bit of a, I'm gonna have to take a little bit of a leap of faith here that you guys watched it. So something called a bulk modulus. It's kind of related to the modulus of elasticity for, but not really, for a material. So, but it's denoted as a big E. In the notes, it's defined as the change in pressure, negative change in pressure, just because down is negative, you know, it's a sign convention, times the change in volume over the volume, okay? So it's telling us that it's machine oil. What do they want? So we got to rearrange this.
What's delta V?
That's what we got to find out. So,
V is just, right?
oh, it's just change in volume.
A change in volume over.
For the fluid of interest.
So it's change in volume over volume.
Yeah, yeah. So the bulk modulus of a fluid is defined by this equation.
Okay.
It's just the definition of it. So if we rearrange this, because we want to find the new volume and the magnitude of the force. So we're interested in this guy, right? Is equal to negative change in pressure divided by the bulk modulus over the original volume. If we go into the back of the book for specified values of things, it will tell us that the bulk modulus for motor oil is 1,303 MPa in metric, or 189,000 PSI. Again, these are just published values. It'll be in the back of the book. If you care, which you do, because I know you do, if this is on a test, it will be given to you. So, what's this negative change in pressure? It's equal to, because originally there's no pressure on it, right? And it tells us that there's going to be, we're inducing a pressure of 27,579 kPa minus 0. Because again, the original pressure that was put on it is nothing. Hi, Mom. So we've got negative 27,579 kPa. Again, this is just metric. It's asking us for both metric and imperial, but we'll get to it. So this is the original volume was 1 liter, 1.000 liter. So they're going to want things in 3 decimal points. So what do we have? We've got change in pressure, we've got the bulk modulus, and we've got the volume. So the change in volume is equal to negative 27,579
All that?
kilonewtons per meter squared divided by,
Did you just know the volume?
it tells us at the beginning of the, what the original volume is 1 liter.
Okay.
Yeah. So what do we have here? Change of volume, 1,303. This is going to be fun. Let's change everything into, change this MPa into kPa. So 10 to the 3 kilonewtons per meter squared. Divided by 1 liter. We keep it, yeah, let's keep it in liters. So meters cubed. Let's do it in per, well, doesn't really matter. Because the, doesn't really matter. Let's keep it in 1 liter. 1 liter. Why do I say it doesn't matter? Because these units cross each other off, right? Okay. I'm writing off the page here. The camera can't see, so I'm gonna flip the page here. Back to that change in volume. So we go negative 27,589 divided by 1,303 times 10 to the 3. To the 3. Get equals, so the change in volume as a result of this induced pressure in metric is going to be minus. So remember there's that lovely little minus sign in there. 0.0212 liters. Okay, so it reduces its volume by a little bit, but still. So what's the new volume?
How did you get that answer? 0.02.
Just using that equation. So if we did that minus 27,000,
I didn't know it was times 10 to the third. The E.
Because we converted from megapascals to kilonewtons.
yeah, so in the notes, and this is just something like the bulk modulus is defined by this equation. All I did is I just rearranged it. These are published values, the bulk modulus, and it's telling us that it is machine oil. So in the back of the book, it published these 2 values, both in metric and in imperial. Go along. We got the change in pressure. We got the original volume. We found out the change in volume. Flip. So we've got the change in volume, but we don't necessarily know what the new volume is yet. And it's the original volume, so at 1.00 liters minus 0.0212 0.0212 liters. So this is going to be 1 second answer. 0.978.
Isn't that a, wouldn't that be a negative and then changes into?
Yeah, so it's changing, it's reducing its volume, which is normal, that if you put a force or pressure on a fluid, it's going to compress the fluid, right? So it's going to reduce the volume from its original volume. Does that make sense? You know, it's one thing to have these equations at your disposal. It's another thing to visualize it and actually trying to think of it as a real physical thing. You know, it's sort of like a little gut check, right? For this problem here, there's oil, its original volume, they put in a volume, it's going to compress, you're going to get a smaller volume. So that might help you think about whether you add it or you subtract it, instead of just, you know, blindly following equations. I've seen things go wrong one too many times with people blindly following equations. Okay, you just gotta and again, lots of times you might not, and you might not know that right away unless you do these calculations a million times, or you somebody tells you and how you have access to it, which is why you're paying the big bucks for the schooling, even though it's online. One day we'll meet. One day we'll meet. I hold out hope. Okay, so we got the new volume. It's also asking us for the force. So remember that force on the bottom of the vessel here. Okay. So what do we have here? I'm going to do all these calculations in metric first, and then we'll go back and do it in the imperial, okay? So what do we have? Pressure equals force over area, right? So if we rearrange this, force equals pressure times area. So what do we have? Our force on this bottom here, boop, it's going to be, what do we have here? That pressure was the induced pressure, it says in the problem, 27,579 kilonewtons per meter squared, kPa. In the area, it's a cylinder because it's given it to us 0.2 of a meter diameter. So pi over 4 times 0.2 meters squared. Area of a circle, 27,579 times 3.14 divided by 4 times 0.2 squared. So meters squared, we're going to come out with something in kilonewtons. All right. 865.981. Again, do that right? I missed something. Okay. So that's the answer. We've got the answer. It's asking us for the new volume point and the force. So that's on metric. Half the equation solved. So let's do it in imperial. Gross imperial. So, I mean, you could go through and convert everything, the diameter and everything in imperial, or you can look at different factors, published factors. So 1 liter is equal to 61.02 cubic inches. Again, I think that these conversion factors are published in the book. My camera is sitting on my book, so unfortunately I can't grab it, but it's also available in a lot of my conversion factors. I just use the Steel Handbook. We've got a lot of that stuff in there, or you can find it online. Again, just be careful what you're using online. It might be a bunch of malarkey. So we know the new volume, 0.9788 liters. We can multiply that. What is this? 1 liter. 1 liter equals 61.02 cubic inches, right? 0.9788 times 61.02. 59.73 cubic inches. So now you could have put it in feet squared too. So it's a little bit, yeah, since we're using liters and probably inches is a little bit more appropriate as opposed to feet, just because of the volumes that we're looking at. They're not, you know, it's not a giant volume. In which way, both answers would be correct if you use the conversion for feet. Life goes on. And then the fourth, then we're going to use the same equation, pressure times area. So the area is going to be a little bit weird. We got to convert the diameter at 0.2 of a meter. We'll flip the page here. I'll flip the page just so that you guys can see. So force equals pressure times area. What's the area? The diameter is 0.2 of a meter. And again, this is just like weird little conversions that we've got. Times 39.37 inches per meter. Again, this is just like a conversion you can find. So what do we got? 0.2 times 39.37, 7.87 inches. So our force is going to be, what do they give it to us, right? 4,000 pounds per square inch, PSI, times pi over 4 times 7.87 inches squared. Good. So 4,000 times 3.1714, sorry, divided by 4 times 7.87 squared. And what we're going to have here, inches squared, we're going to come up with pounds. It's looking good. It's the right units. We got 194,770, wow, yeah, 478 pounds. So, mystery solved. You got both metric and imperial. Yay. So that's the first unit's problems done. Like I said, I'll publish the answers, but you guys all have, and like I said, I'll put up this lovely little video. Now I'm just going to move on to the second unit. Thank you all for staying, for those of you who did. Okay. So if we look at unit 2, viscosity, and we go into those notes. It'll take a second to load up here.
What's the topic for this one?
So if you look in week 1 in that same folder in the content, there is a PDF version. It's called Unit 2 Viscosity. Again, this probably would have made more sense if you saw the lovely video and read the notes. But like I said, absorb it later. You got time. So I'm just gonna So viscosity is just it's measuring how resistant a fluid is to shear stress, more or less.
Okay.
So if I look at page 32, problem 1, there's only, I think, 2 problems in this one, so won't take much longer. You guys are probably hungry, it's lunchtime. So we got problem 1, a 30 millimeter diameter ball fell 43.6 meters in 1.5 seconds. Wowzers. The temperature of the fluid is 20 degrees C. The specific gravity of the ball is 1.9, and the specific gravity of the fluid is 0.94. And they're going to ask us what the fluid is. Okay. So again, watch the video, read the notes, and this will make a little bit more sense. But here we go. We've got a lovely little vessel. You drop a ball into it, it falls down. Surprise, surprise. And it's going 43.6 meters. That is crazy. Just, it's crazy because I think the height, is just because the height of the vessel is really, can you imagine a almost half a meter vessel? Any which way. So the ball is 30 millimeter diameter. The time it takes to travel is 1.5 seconds. The temperature is 20 degrees C, which is sort of like the base temperature for a lot of these recorded values for different fluids. So the specific gravity of the ball is 1.9. The specific gravity of the fluid is 0.94. It's going to ask us what the fluid is, okay? Just by doing this, what is called a fall test. I think it's in the, let's have a look, see what does it call it? Stokes law and all this lovely little stuff. Falling ball viscometer, that's it. Okay. So velocity is just distance over time, right? So we know that it's falling 43.6 meters over 1.5 seconds. So form that lovely little calculation. We get 23.568 meters per second. Specific weight of the fluid is the specific gravity of the fluid times the specific weight of water, 4 degrees C. So what is that? 0.94 times 9.81. Let me know if that noise outside is getting too much for you. I can go and close the door. So 0.94 times.
Closing the door? It feels like I'm in a construction site.
Pardon me? Sorry? Oh.
Would you mind closing the door? It feels like I'm in a construction.
Yeah, sure. Okay, hold on. One moment.
Yo, who's thinking about capstone? Nobody?
Hopefully that's better. They're doing some renos across the street, so it's gets a bit much sometimes for sure. Okay. Where were we? Okay, 0.94 times 9.81 kilonewtons per meter. Okay, so we got 9.221 kilonewtons per meter cubed. And the specific weight of the ball is the specific gravity of the ball times unit weight of water. So what do we have here? 1.9 times 9.81 kilonewtons per meter cubed. 1.9, 9.81. This is equal to 18.64 kilonewtons per meter cubed. And we've got the diameter of the ball. Okay, I'm gonna flip. Da-da. So what are they asking us for? What is the, so the dynamic viscosity? Again, this would make a lot more sense if you saw the video, but don't worry about it. Viscosity. It's denoted by this eta, squiggly little n. Okay. So it's equal to, and it's defined as, so this is that Stokes law business. It's a formula that's in there. It might be in, I think I published the final formula sheet too for you in D2L. That might, I mean, don't get too worked up about it now, but familiar, a lot of these formulas are in there. So it's the specific weight of the solid minus fluid times the diameter of the ball squared, 18 times the velocity. Okay, so we've got all these little components. 18.64 kilonewtons per meter cubed minus 9.22 kilonewtons per meter cubed. The diameter of the ball, 0.3, tell us, millimeters. Okay, so 1, 2, 3, there it is. This will be in meters. Meters, regular meters. Meters, but the whole thing is squared, divided by 18 times 29.07 meters per second. Okay, so this is a little bit more of a calculation. 18.
That 30 millimeter became 0.3 meters.
Yeah, because everything's in meters already, so it's easier to convert the millimeters into meters now. Otherwise, you'll get some sort of
0.0.
funky. So 18.64 minus 9.22 times 0.03 squared. Boop. We're going to divide that by 18 times 29.07. And equals, what do we get here? 1.62 times 10 to the negative 5. Goofy. And what do we have here? We're going to have kilonewtons per meters cubed times meters squared divided by meters per second. So we're going to have cheese and rice. KPA seconds. Because of this lovely little kilonewton thing. And that's the unit, metric unit for this eta. So this is also equal to, because it's negative 5, let's put it in PA, okay? So 1.62 times 10 to the negative 2 Pascal seconds. Hopefully, well, maybe we'll just go over this unit thing real quick. Well, not quick, but what do we have? We had kilonewtons per meter cubed times meters squared, right? Divided by meters per second. So this guy goes away, that guy goes away. We got 1 meter here. So this is equal to kilonewton per meter times seconds per meter equals kilonewtons per meters squared times second. So hopefully that makes sense on how we got this little leap of faith. Okay. So if we go into the back of the book in the published values for a fluid that has a dynamic viscosity of 1.62 times 10 to the negative 2 Pascal seconds. And you'll see in there, the fluid is going to be, oh geez, ethylene glycol. Don't ask me what that is. I have no idea. Somebody knows. Maybe I'll find out before next class.
You get high from it.
So 1 mystery solved. Problem 2. Find the dynamic viscosity and the kinematic viscosity for this lovely little problem. So what do we have here? We've got fluid. This surface is stationary. The fluid between the stationary bit and a plate that is moving. What do we have this? It's 2 millimeters in depth. The area of this plate is equal to 3.0 meters squared. There's a force acting on it, 270 newtons, with a velocity of 0.5 meters per second. The fluid is oil, and it has a density of 900 kilograms per meter cubed. So they want to know the dynamic viscosity and the kinematic viscosity. So the shear stress on the fluid as a result of this plane moving, okay, is like tau, the same as like your mechanics course, right? Force over area. So tau is equal to 270 newtons over 3.0 meters squared. 270 divided by 3. So we got 90 pascals, Newton per meter squared. And the other thing, joys of shear stress on a fluid is equal to eta times the change in velocity over the change in height. So this height is defined from the stationary point, okay? So it's going to be the same boundary conditions for this, right? If you look at, let's get another color. Got some colors left over from previous course, great. So in this case, they're idealizing the velocity gradient as linear. So the change in velocity along this height is linear. And at the boundaries, it's the same as the boundaries of the the velocity is the same as the boundaries that are it's being induced. So basically the velocity at the stationary boundary is 0. At the top here, it's going to be, what is it? 0.5 meters per second. Okay. So what do we know? Here we go. So we'll call this point 1. And we'll call this point 2. So stationary point 1, moving plate point 2. So what do we know here? Boop, boop. The velocity at point 1, 0 meters per second at y equals 0. Okay? y1 equals 0. Okay, so therefore, again, we'll take this nice step by step. The change in velocity over the change in height, so that velocity gradient is going to be v2 minus v1 over y2 minus y1. Makes sense? So 0.5 meters per second minus 0 meters per second. Again, the boundary conditions, it's the sort of the definition of velocity gradient and induced velocities on fluid. It's going to be 0. So y2, it's only 2 millimeters. So 0.002 minus 0 meters. Okay. So what is our velocity gradient is 0.5 divided by 0.002. So 250, and what units are we going to get? Meters per second. So this is per second, or 250 second to the -1. See that? Okay, I'm going to flip. So if you recall, shear stress is equal to eta times the velocity gradient.
What is that stress's name? Shear stress?
Yeah, it's just a shear stress. I mean, the plate. So basically, I mean, it's not overly, if you look at the figure and the problem, I'll draw it out for you. There's like a fluid gap, right? And then there's a plate that's being moved on it. So it's just the shear stress in the fluid as a result of the force being applied on this plate.
Okay.
If you want to kind of visualize what's actually going on.
Yeah, what's the N symbol?
It's eta, it's that same thing. It's flip, going up. Come on.
Is it some constant?
Yeah, it's a constant for it's a constant for a Newtonian fluid. Again, it makes more sense if you go through it. It is a constant, yes, for fluids that behave in that manner. If you remember from your mechanics and materials course,
Yeah.
I'm just going to do a list right now. Remember how there was, I mean, it's just a little bit different because fluids aren't exactly like solids because their molecular spacing is different, and they're not as cohesive as a solid. I mean, I guess you kind of know that. But if you remember for steel, right? We've got this lovely little, what is this thing? I can draw it. We got stress over strain, right? And then this modulus of elasticity is linear. But that's just this is a steel one, right? Like it's not the same for all, this slope or how it behaves isn't the same for all materials. It's the same for fluids, right? their resistance to shear stress sometimes are linear, sometimes are not. Like you can think about ketchup. It's a good example.
Yeah.
You gotta, like, you know, if you have Heinz or whatever, and you're trying to like get it out of a bottle, and it doesn't go until either you put a knife up the ketchup or you give it a pat on the bottom of the bottle.
Yeah.
So it doesn't move really until you give it enough force in order for it to move. So it doesn't necessarily behave in a linear manner.
Yeah.
It's watch the video. We talk about honey, ketchup, water.
I watched the video. All right.
Yeah, okay, good.
Sounds good.
So, yeah, so in this case, it's assumed to be a Newtonian fluid, so that it is linear. Exactly. Okay,
Okay.
back to the problem at hand, I guess. Does that answer your question?
Yeah, I was just worried about the end where it came from randomly in the equation, and I don't know what it is.
Oh, okay, yeah. That's what we're finding out.
Okay.
We're solving this problem, okay? Because it wants us to find the dynamic viscosity and the kinematic viscosity. So there we go.
Yeah.
Hiding. Hold on. Do. Just have to look back at my notes and see where I'm going. Okay, that's where I'm going. Okay.
How long are you gonna be on this class for?
Pardon me?
How long are you gonna take more, like, on this class? Because the class I think.
We got probably another 10 minutes of calculation,
Okay.
I guess. So if we take this equation and we rearrange it, so we've got eta equals the shear stress over the velocity gradient, right? And so that's what we're trying to find. We've got the shear stress. We calculated that, right? That's at 90 pascals, so newtons per meter squared. And we've got our velocity gradient, which was that 250 per second. 90 divided by 250. Got 0.36 Pascal seconds. So the units work out. Good. So that is the dynamic viscosity. And now we're going to find the kinematic viscosity. So it's like a stylized V.
Symbol for dynamics viscosity.
Yes. So
Okay,
we solved the first part of the question. Now we're looking for the kinematic viscosity, which is that funny little V.
What does this mean, though? What does viscosity really mean? Is it like the ability of liquid to flow in a certain speed, or what?
Yeah, it's a fluid's resistance to shear stress. So the more viscous a fluid is the less resistant to stress. So water is very flowable.
So it's
Honey is a little bit less flowable, so it's got a
higher viscosity.
yeah. And then ketchup is even higher than that.
Oh, okay.
Yeah, it's like how much, how resistant it is to shear stress and basically like how it flows. Makes sense?
Yeah.
Okay, so kinematic viscosity is defined by the dynamic viscosity over density. Straighten you out here. Okay, so we've got this 0.36 Pascal seconds divided by, and we're told, the density is 900 kilograms per meters cubed. So what do we got here? Divide that by 900. What do we got? 4.0 times 10 to the negative 4 meters squared per second. How did we get meters squared per second?
Where did you get the 900 number?
That's defined in the equation too. Tells us that the density of the fluid is 900 kilograms per cubic meter.
Which fluid, like whatever fluid or like some of the fluid?
It says, well, the whole fluid, so that 2 millimeter depth of fluid.
That's just given in the question.
Yes.
Okay, that's fine.
So I'm just gonna do this real quick too, how we got. Woo,
Can I see the
this
bottom
one,
part?
you know, because the kinematic viscosity is in meters squared per second. So how did we get that in Pascal seconds divided by kilograms per meter squared? So we got newtons per meter squared divided by kilograms per meter cubed. Okay, and a newton is a kilogram per meter per second, or kilogram meter per second squared times 1 over meter squared times seconds over kilograms per meter cubed. So what do we got here? This goes, that goes, that goes. Now we got meters. So what do we have? Clean this up a bit. Kilograms, seconds, meters, times, flip that over, meter cubed, kilograms, boop, 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 boop. So meters squared per second. That's where we get those weird units for. Okay. That was a long class, you guys. But we did it.
Does it get harder than this?
Oh yeah, they're gonna get way harder than this. This is the first week. It's gonna get more difficult. But like I said, the plan is to have the videos, the lecture videos, and the notes up by Monday at 10:30. They might be up sooner, but I always send you guys an email and put it on the D2L, both forms of communication, so that you know when they've been posted. So if I get them done sooner, you'll have access to them sooner. And then every Wednesday, we'll just do the problems. It's a little bit, I'm sorry that it took so long, but I had fun, you guys. So you'll have an assignment that's gonna be posted. I'll do that right after this class. I might have some lunch first, but again, I'll send you an email and it'll be on D2L. And yeah, it'll be like, I'll put it on a news item as well as an email. So it'll be posted like you'll know that it's up that way. If you're not getting the emails, send me but you guys got this one, so obviously you're getting some emails. But just let me know and then I'll send it to you. But I'll post this video, I'll post the solutions, and you'll get an assignment. The assignment won't be due until next week before 10:30. Okay. And I think that's it. I think we got it. Do you guys have any questions? Are you good? You're hungry. It's been a long time.
Yeah.
Okay, thanks you guys.
Are the assignments like kind of going to be similar to the problems that you're doing?
They might be a little bit more difficult,
Oh, shit.
but it'll all be based on the notes.
So
if you have the book, do you have the book?
yeah, we have the book.
Okay, good.
We're having
Yeah.
problem solving a question and it's like too hard for us. I don't know.
It won't, yeah. It's a first year fluids course. I'm not gonna, and they're gonna be harder. You know, these are just like all like, you know, when you do the questions in the classes,
Yeah.
assignments are always a little bit harder. If you have any questions, just text me. You have my cell phone number, I think, is in the course notes, so in the outline. So just text me, and then either we can arrange a phone call or a
Zoom.
yeah, a Zoom, or I'll just text it to you, and hopefully we'll get it sorted out. Like I said,
Okay.
I'm here to help you out, not to hinder.
That's
Okay.
Good to hear.
Especially given our challenging learning environment.
Yeah.
We're gonna hopefully, hopefully all the instructors are trying to help you out a little bit more than, and unfortunately, like on one hand, yeah, you have access to me whenever you want, but on the other hand, it's not like, you know, we're physically sitting there in school.
Yeah.
But we all get to work in our pajamas as a result.
That's fun times. That's so fun times. I waste so much less time. All I have to do is get up and like turn my computer on.
I know, it's kind of a funny little thing, isn't it? The travel time. It's like on one hand it's bad, but on the other hand it's kind of good. It's looking at the bright side of things right now.
Yeah. Thank you.
Okay, you guys. Oh, if you have any questions, let me know.
Are we gonna be on for next year, like on campus?
I have heard that they're not going to open up the campus until like fully until there's a vaccine. I mean, everything's changing all the time, right? I thought for last summer, because I did a summer course with some of your co-students, and I thought for sure we'd have at least the final together because there'd be enough space and whatever, but they never did it. I think but you guys do have soils labs, I think, live, right?
Yeah, I already did it last year, so I don't have to do it again. But the
Lucky
second
you.
year I have to do it again. I'm just gonna ask Bao if I pass the labs portion, then I'll just do the test online. And then I wouldn't even have to come there for like just for one class.
Yeah, yeah, yeah. I guess it's up to each instructor. I know
So
the school wanted like
Zoe's,
you have to do emergency plans if you wanted to actually physically be on campus. So
yeah.
I think it's easier for you guys. Oh, I don't know. Everybody's different.
I just want to pass with a diploma. That's it. I don't care like how good I do. Like,
C's get degrees. I say it all the time.
I saw my friend like Gagan. He barely passed. Like he was like such a bad student. He got in with like City of Surrey. He's like assistant engineer. Like he looks at like so many things. I'm like, you did nothing in school.
Well, that's the thing.
Like he was smart. Like he needed less time to like look at stuff to
Yeah.
like understand and do it.
Mhm.
And that's what he did. Like he didn't study at all. He would just look at it one time and then do the test.
Yeah. Yeah. I think I cared a lot about marks when I was in tech school because I wanted to do the bridge and you had to get, you know, the good marks to do that. And then once I got to UBC, it was like completely different learning environment. And yeah, I think you know, you start getting your marks back and you're like, oh, it's not as good as when I was in tech school, but I just kept saying C's get degrees. And yeah, when you go and look for work, everybody's assumed, they all passed, right? So you
Yeah.
all have the same
Knowledge.
level of knowledge. It's just your personality and whether you're going to fit into the organization or whatever. Hence why I work by myself. I don't fit into any organization.
Really?
No, well, kind of. You've probably heard that engineering isn't super great for women, and I'm here to tell you it's not.
I don't know. Do you know about Main Road?
Main road?
Yeah, Main Road Contracting.
No.
They're here in Lower Mainland.
Oh, okay. Oh, is that
Uh-huh.
where you're on? You're on the.
I was doing a co-op with them.
Okay.
Yeah, we were inspecting culverts.
Oh, yeah.
Yeah, it was fun.
Yeah, you'll find this interesting because we do some culvert design. So you'll have had some real world knowledge. That'll be great. That'll be fun.
I've done some inspections, so like I know what they look like and how bad they are and all that
You
stuff.
got a leg up on everybody else, that's for sure.
I made an Excel file of like 400 like culverts, and then there are like all the details in there, like rotting or like is it like all the different criteria you have to label it from like 10 different things.
Yeah, yeah, yeah. Good portion of our work is inspection of existing infrastructure, especially since it's all aging and getting old and yucky and stupid. But it keeps us busy and employed.
Yeah.
I'm not I was kind of, when COVID first started, I was a little bit worried for you guys about whether there'd be work or not for you, but it doesn't seem like construction or engineering is stopped by any stretch of the imagination. So everybody I know is still busy, got lots of work. So the future looks pretty good for you guys.
Yeah, I hope so. It's gonna be that way.
Yeah, and you have that's the other thing. If you have a co-op term already, or work term, or however you got it,
Mhm.
then you're laughing.
Yeah. Why?
Well, laughing as much as you can laugh, I guess. Okay, thanks guys. Expect an email from me later on today.
What?
Okay, have fun.
All right.
Bye.